somewhere above the western Atlantic Ocean. If you could rise high enough to see the whole curve of the Earth, you would notice something. The ocean down there is not all the same. There are places where the water runs deep blue, almost violet. There are places where shallow banks glow pale green in the sunlight. And somewhere in that wide stretch of warm water between Florida, Bermuda, and the islands of the Caribbean, there is a region that has carried a strange weight for a very long time. Before we go any further, if you want a brand new Earth topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. That region has a name most people recognize the moment they hear it. The Bermuda Triangle. 3 words that carry more questions than answers, more theories than conclusions, more open water than any map can quite explain. From that imagined height above the Earth, the triangle looks like nothing special. It is simply ocean. Warm, restless, endlessly moving ocean. The water there is part of the Atlantic, one of the great bodies of water that wraps around our planet. Sunlight hits its surface and scatters into 1,000 shades of blue. Clouds drift over it in slow white shapes. Beneath the surface, currents pull in directions that are not always obvious from above. And yet, for decades, this particular stretch of ocean has drawn questions the way a flame draws moths. Ships have gone missing there. Aircraft have vanished. Crews have disappeared without leaving much trace. Some of those disappearances have clean explanations. Some do not. And that gap between what we know and what we cannot quite account for is exactly where the mystery lives. The shape of the triangle is not official. No government body has drawn its borders on a chart. No international maritime organization has marked it as a special zone. The shape comes from writers and researchers who, starting in the middle of the 20th century, began to notice a pattern, or what looked like a pattern, in the records of ships and planes that had gone missing in that part of the world. They drew lines between 3 points: the southern tip of Florida, the island of Bermuda, far out in the Atlantic, and the island of Puerto Rico to the southeast. The rough triangle those lines formed covered somewhere between 500,000 and 1.5 million square miles of ocean, depending on who was drawing it. uncertainty in the size is itself worth sitting with. The triangle has no fixed shape. Its edges shift depending on the source. One researcher draws it one way, another draws it differently. Some versions include the Bahamas, some reach further east. The region is, in a sense, as much an idea as it is a place. But the ocean beneath that idea is very real. It is one of the most heavily traveled stretches of water on Earth. Ships cross it constantly, carrying cargo between the Americas, the Caribbean, and Europe. Small boats sail through it every season. Aircraft fly over it daily. The skies above it are busy. The sea lanes below are well worn. And that fact matters enormously to the question at the heart of this story. When researchers began to look carefully at the actual records, the insurance claims, the Coast Guard reports, the accident logs, some of them found something surprising. The Bermuda Triangle, by certain measures, does not lose ships or planes at a rate higher than other busy stretches of ocean. Some analyses suggest the losses. There are roughly what you would expect given the volume of traffic passing through. Other researchers push back on that conclusion. They point to specific cases that seem genuinely hard to explain. Cases where experienced crews vanished in good weather. Cases where aircraft disappeared without a distress call. Cases where the evidence simply ran out before it reached any clear answer. So the question is not settled. It may be that the triangle is a myth built from coincidence and amplified by storytelling. It may be that something about that particular stretch of ocean, its weather, its geology, its currents, its depth, creates conditions that are genuinely more dangerous than average. Both ideas have serious people behind them. Neither has fully won the argument. That is where we begin tonight. Not with a verdict, not with a tidy answer, but with the open water itself, stretching out in every direction under a warm sky, holding its secrets in the way that deep water always does, quietly, patiently, without any particular hurry to explain itself. The mystery is real, even if its shape keeps shifting. And there is something quietly wonderful about that. Picture a triangle drawn on the surface of the Atlantic Ocean. One corner sits near Miami, on the southeastern tip of Florida. Another corner reaches down to the island of Puerto Rico, roughly 1,000 miles to the southeast. The third corner stretches northeast to the island of Bermuda, floating alone in the open Atlantic, about 1,000 miles off the coast of North Carolina. Connect those 3 points, and you have the shape that has carried this name for decades. The area inside that triangle is enormous. Most estimates put it somewhere between 500,000 and 1.5 million square miles, depending on who is drawing the lines. That range matters because the triangle has no official borders. No government body has ever formally defined it. No maritime chart marks it with a dotted line. The boundaries shift depending on the source, and that looseness is one of the first things worth sitting with. We are talking about a region that exists, in some ways, more as an idea than as a fixed place. To feel the scale of it, consider this. The entire state of Texas covers about 268,000 square miles. Even the smaller estimates for the triangle are roughly twice that. The larger estimates would cover nearly 6 Texas-sized spaces laid side by side. That is a vast stretch of open water, and most of it is deep, very deep. The ocean floor beneath the triangle is not flat. It is a mix of shallow coastal shelves and sudden, dramatic drops. Near the Bahamas, the water can be as shallow as a few dozen feet, so clear and pale blue that you can see the sandy bottom from the air, but move further out, and the floor falls away quickly. Parts of the Puerto Rico Trench, which runs along the southern edge of the triangle's territory, reach depths of more than 27,000 feet. That is deeper than Mount Everest is tall. The water down there is cold, dark, and almost entirely unexplored. Bermuda itself sits at the triangle's northern tip. It is a small cluster of islands, the remnants of an ancient volcanic seamount, a mountain that rose from the ocean floor long ago and then stopped growing, leaving just its upper peaks above the waterline. The island sits alone, far from any continent, surrounded by open Atlantic on all sides. Sailors have used it as a waypoint for centuries, partly because of its position, and partly because there is simply nothing else out there for hundreds of miles. Miami anchors the western corner. It is one of the busiest ports in the world, with ships and aircraft moving through the region constantly. Puerto Rico, at the southern corner, is a major hub for Caribbean shipping and air travel. The triangle, then, is not some remote and rarely visited patch of ocean. It sits directly across some of the most heavily traveled routes in the Atlantic world. That fact becomes important later when we look at what the numbers actually say about how many vessels pass through and how many are lost. The name itself is relatively recent. The phrase Bermuda Triangle was first used in print in 1964 in a magazine article by a writer named Vincent Gaddis. Before that, the region had no single name, though stories about strange losses in the area had been circulating for years. The name stuck quickly, and within a decade, it had spread into books, television programs, and popular conversation around the world. The triangle became a cultural landmark before anyone had done a careful statistical study of whether it deserved the reputation at all. That is one of the quiet puzzles underneath this whole subject. The name came before the evidence was properly examined. The story took shape before the data was gathered. Some researchers argue that this order of events matters enormously. They suggest that once a name and a story exist, people begin fitting events into that story, whether or not the events truly belong there. Others push back on that. They point to accounts that predate the name by many years, to ships and planes that vanished in ways that still resist easy explanation. They argue that something about this stretch of water, its weather, its geography, its currents, or something else not yet identified, creates conditions that are genuinely unusual. Both views are still in play. The triangle sits there either way, stretching across the warm blue Atlantic between those 3 points. Miami to Bermuda, Bermuda to Puerto Rico, Puerto Rico back to Miami. The shape is simple. The questions inside it are not. And as we settle into the story of this place, it helps to hold that shape in mind, that vast, loosely defined, heavily traveled patch of ocean where the water can go from shallow and sunlit to impossibly deep within just a few miles. To understand the Bermuda Triangle, it helps to go back, not just a few centuries, not just a few thousand years, much further than that. The ocean beneath this stretch of water has a story that began long before any ship ever crossed it, long before any human eye ever looked out at its blue surface and wondered what lay below. The Atlantic Ocean is, in geological terms, a relatively young ocean. The floor beneath the Bermuda Triangle sits on crust that formed as two ancient landmasses slowly pulled apart. That process, called seafloor spreading, happens when the deep rock beneath the ocean cracks open along a central ridge, and new material wells up to fill the gap. The Atlantic has been widening this way for roughly 180 million years. The rock beneath the triangle is old, but the ocean itself is still growing, still stretching, still moving in ways we can measure, but don't fully understand. What makes the seafloor here unusual is its variety. The Western Atlantic is not a flat, featureless plain. There are deep trenches, wide, shallow shelves, and sudden dramatic drop-offs where the ocean floor plunges from a few hundred feet to several thousand. The continental shelf, that broad, gently sloping ledge that extends from the coastline before the ocean floor falls away, is particularly wide along the eastern coast of North America. Ships crossing the triangle pass over water that changes depth dramatically over short distances. One moment, the ocean beneath them might be a few hundred feet deep. A short distance later, it could be a mile or more. That shift in depth matters. It shapes the currents. It shapes the weather. It shapes the way water moves through this part of the world. And some researchers believe it may shape the conditions that make this region feel, to some, like a place apart. The Bahama Banks, a vast system of shallow limestone platforms just to the south and east of Florida, are part of what makes this corner of the Atlantic so geologically distinctive. These platforms are ancient. They built up over tens of millions of years as coral and marine organisms grew, died, and accumulated layer upon layer. The limestone beneath the Bahamas is thousands of feet thick in places, and within it, carved by water over immense stretches of time, are caves and tunnels and chambers. Some of those chambers open directly to the ocean floor in the form of what are called blue holes, deep, circular shafts that drop straight down into darkness. They look from above like deep blue circles cut into the lighter seafloor. What exactly happens inside the largest and deepest of them is still being studied. The sediment on the floor of the Western Atlantic is also worth considering. In some areas, it is thick and soft. In others, the rock is bare and hard. Where the sediment is deep, it can trap gases, particularly methane, a gas produced when organic material breaks down in low oxygen conditions deep below the surface. The methane doesn't always stay trapped. One hypothesis, and it remains a hypothesis, not a settled explanation, is that large releases of methane from the seafloor could, under the right conditions, affect the water above. Some researchers have proposed that a sudden release of enough gas could reduce the density of the water so sharply that a ship might lose buoyancy very quickly. Others are skeptical. They point out that no confirmed methane eruption has ever been directly linked to a ship's disappearance in this region. The debate remains open. What is not debated is the sheer depth of geological time written into this ocean floor. The rock, the sediment, the limestone banks, the hidden caves, all of it accumulated across spans of time that are almost impossible to hold in the mind. A single layer of seafloor sediment, an inch thick, might represent thousands of years of slow accumulation. The blue holes took millions of years to form. The Atlantic itself has been opening since before the age of dinosaurs. When a ship or a plane disappears over this stretch of water, it disappears into something ancient. The ocean here is not a simple, uniform body of water. It is a complex, layered, geologically active system with features that are still being mapped, still being understood. Some of those features may be entirely irrelevant to any disappearance. Some may not be. The honest answer is that we are still learning what the seafloor here looks like in detail and what it might be capable of. The ocean beneath the Bermuda Triangle has been here far longer than the mystery. It will be here long after the mystery is either solved or quietly set aside. For now, it keeps its own counsel, deep and dark, and patient below the surface. The air above the Bermuda Triangle is not ordinary air. It carries the same nitrogen and oxygen that fills every breath you take tonight. But the way that air moves in this part of the Atlantic, the way it gathers, shifts, and sometimes collapses without warning, is something meteorologists have studied for decades without fully explaining. Start with the warmth. The surface water here is very warm, especially in summer. The Gulf Stream pushes hot water up from the tropics, and that heat rises into the air above it. Warm, wet air is lighter than cool, dry air. It lifts, and when it lifts fast enough, it pulls cooler air rushing in beneath it. That is how storms are born. The triangle sits in a place where this process happens often, and sometimes violently. Hurricanes form in this general region of the Atlantic. They are enormous, slow-spinning storms that can stretch for hundreds of miles. A ship caught in one has almost no warning if its radio fails. A small plane caught in one may not survive, but hurricanes are visible. They show up on maps. They have names. They are not the strangest thing the triangle's sky can produce. The stranger thing is the microburst. A microburst is a sudden, powerful downward rush of air that falls from a storm cloud toward the sea. It can hit the water at speeds of more than 100 miles per hour. It is fast, localized, and sometimes nearly invisible on radar. A plane flying through a microburst can lose altitude so quickly that the crew has almost no time to respond. Some researchers believe microbursts may explain certain aircraft disappearances in the region, cases where a plane vanished from radar without a distress call. Others point out that microbursts occur all over the world and do not explain any particular concentration of incidents here. Then there is the question of waterspouts. A waterspout is a rotating column of air and mist that forms over water, similar to a tornado over land. The triangle's warm, humid air creates ideal conditions for them. They can appear quickly and disappear just as fast. A small vessel caught in one could capsize. A low-flying aircraft could be thrown off course. Waterspouts are real, documented and common in the Caribbean and the Western Atlantic. Whether they have played a role in any specific disappearance is, in most cases, unknown. Some researchers have pointed to something called a fata morgana. This is a type of mirage that forms over warm water when layers of air at different temperatures bend light in unusual ways. A fata morgana can make a ship appear to float above the horizon. It can make land appear where there is none. It can make a clear horizon look like a wall of fog. Sailors have been confused by these illusions for centuries. One theory holds that fata morgana mirages may have contributed to navigational errors in the triangle, leading ships or planes off course. The competing view is that experienced navigators and pilots learn to recognize mirages, and that this explanation, while interesting, does not account for the most serious disappearances. The atmosphere itself carries a kind of history. The oxygen in the air above the triangle was made by ancient plants and ocean organisms over billions of years. The nitrogen was released by volcanoes and biological processes long before humans existed. Even the water vapor drifting through these clouds began somewhere else, evaporated from the ocean surface, lifted by heat, carried by wind. Everything in the sky above this stretch of sea has traveled a very long way to be here. That water vapor is worth thinking about. The Atlantic in this region produces enormous amounts of it. Warm, moist air rising from the sea can build a thunderstorm in a matter of hours. These storms can be tall, reaching up to 40,000 feet, which is higher than most commercial aircraft fly. Inside a large Atlantic thunderstorm, the turbulence can be severe enough to damage an aircraft structure. The lightning can interfere with instruments. The rain can be so heavy that visibility drops to nearly nothing. And yet, for all of this, the triangle's weather is not uniquely dangerous compared to other warm ocean regions. Storms like these form across the tropics. Waterspouts appear in the Mediterranean. Microbursts happen over the Gulf of Mexico. The weather here is intense, but it is not, by itself, a satisfying explanation for why this particular patch of ocean carries such a heavy reputation. What the sky above the triangle offers is a set of conditions: warm water, humid air, fast building storms, sudden downbursts, that could, under the right circumstances, create serious danger. Whether those conditions have done so more often here than elsewhere is a question the data has not yet settled. There is something quietly strange about the way a compass behaves in certain parts of the world. Most of the time, a compass needle points toward magnetic north, not true north, but close enough that sailors and pilots have trusted it for centuries. The needle swings, settles, and holds. You can build a course around it. You can find your way home. But there are places where the needle does not behave quite as expected. The Bermuda Triangle sits in a part of the Atlantic where the relationship between true north and magnetic north gets complicated. True north is the geographic top of the Earth, the actual pole. Magnetic north is where the planet's magnetic field pulls the needle, and it drifts slowly over time. The difference between the two is called magnetic declination. Navigators have always had to account for it. In some regions, the gap is small. In others, it is large enough to send a ship or a plane meaningfully off course if the navigator doesn't correct for it. For a long time, one popular idea held that the Bermuda Triangle was one of only two places on Earth where a compass pointed to true north and magnetic north at the same time, meaning no correction was needed, and an unwary navigator might not apply one. This idea spread widely. It became part of the triangle's legend. The trouble is, most researchers who have looked carefully at the data say this is not quite accurate. The zone of zero declination, called the agonic line, does pass through the western Atlantic, but it shifts over decades as the magnetic field changes. Whether it sits squarely over the triangle at any given time is a moving target. The question of how much magnetic variation has actually contributed to real losses in the region remains genuinely open. What is not in question is that the Earth's magnetic field is uneven. It has weak spots and strong spots. It has local anomalies, places where the rock beneath the seafloor is rich in iron or other magnetic minerals, pulling the needle slightly off in ways that don't appear on older charts. The seafloor of the Western Atlantic is geologically complex. There are ancient volcanic formations down there, ridges and basins formed over millions of years. Some researchers wonder whether localized magnetic disturbances in the region could have contributed to navigational confusion, especially in the era before GPS, when a pilot or captain had only instruments and dead reckoning to go on. Dead reckoning is the practice of estimating your current position based on a known starting point, your speed, your heading, and the time elapsed. It works well when all those inputs are reliable. When one of them drifts, when the compass is slightly off, or the current is stronger than expected, the errors compound quietly. You think you are here. You are actually there. In open ocean, with no landmarks, that gap can become very large before anyone notices. And that brings us to the current. The Gulf Stream is one of the most powerful rivers on Earth, except it flows through the ocean rather than over land. It moves warm water northward through the Western Atlantic at speeds that can reach several miles per hour. It is wide and deep and relentless. A vessel caught in the Gulf Stream without accounting for its push can be carried miles from its intended course in just a few hours. Any debris from a vessel lost in or near the stream can be swept far away very quickly, which is one reason some researchers cite when explaining why wreckage from triangle incidents is sometimes hard to find. The stream's edges are not calm. Where warm Gulf Stream water meets cooler Atlantic water, the boundary is turbulent. Eddies spin off from the main current. Water temperatures shift sharply over short distances. Some oceanographers note that these boundary zones can produce unusual sea conditions, sudden swells, confused wave patterns, water that behaves unpredictably even under clear skies. Whether these forces working together, a slightly unreliable compass, a powerful invisible current, turbulent boundary waters, are enough to explain the losses attributed to the triangle, is something researchers still debate. Some say yes, that ordinary navigation in a challenging environment accounts for nearly everything. Others argue the combination of factors in this particular stretch of ocean is unusual enough to warrant more study. The honest answer is that no one has drawn a clean line from magnetic anomaly to specific shipwreck, or from Gulf Stream current to specific disappearance. The connections are plausible. They are worth considering, but they remain, for now, theories rather than conclusions. The compass needle points somewhere. The current flows on, and the gap between what we think we know and what we can actually prove stays wide and quiet, like the ocean itself on a still, dark night. There is a particular kind of quiet that settles over a harbor when a ship does not return. The dock workers wait. The families wait. The water just keeps moving, indifferent and wide, offering nothing back. That silence has fallen many times over the centuries in ports connected to the stretch of ocean we call the Bermuda Triangle. And when you begin to count the ships, the numbers start to feel heavy in a way that is hard to shake. One of the most often cited cases is that of the USS Cyclops. She was a massive Navy collier, which means a ship built to carry coal. In 1918, she left Barbados carrying more than 10,000 tons of manganese ore and over 300 men. She never arrived in Baltimore. No distress call was ever recorded. No wreckage was ever found. No bodies. No lifeboats. She simply ceased to exist somewhere in the Western Atlantic. To this day, the loss of the Cyclops remains the single largest non-combat loss of life in the history of the United States Navy. To understand the scale of that disappearance, think of it this way. The Cyclops was about as long as 2.5 city blocks. She weighed, when fully loaded, around 19,000 tons. Imagine a steel building laid on its side and set to sea. Ships like that do not vanish quietly. They leave something behind, and yet she left nothing. The ocean took her completely. Some researchers point to structural problems. The Cyclops had a history of engine trouble, and her cargo, manganese ore, is extremely dense and heavy. If the weight shifted suddenly in rough seas, a ship could roll and sink in minutes, too fast for any signal. Others suggest she may have been lost to a rogue wave, one of those rare, enormous walls of water that can appear without warning, even in calm conditions. But neither theory has ever been confirmed. The sea has kept its answer. The Cyclops is not alone. Her sister ships, the Proteus and the Nereus, were both lost in roughly the same part of the Atlantic during World War II, also without explanation, also without wreckage. 3 ships of the same class, gone in the same general waters, across different years and different conditions. That repetition is the kind of thing that makes researchers pause. It could be coincidence. It could be something about the design of those ships. It could be something about those waters. No one has settled the question. Then there is the Carol A. Deering, a 5-masted schooner found drifting off Cape Hatteras in 1921. Her sails were set. Her lifeboats were gone. Food was cooking on the stove, but every single crew member had vanished. She was a ghost ship in the truest sense, still moving, still warm, but empty. The investigation involved 5 government agencies and produced no clear answer. Piracy, mutiny, and a sudden waterspout were all considered. None was ever confirmed. What makes these cases so difficult to measure is the sheer size of the region involved. The Bermuda Triangle covers somewhere between 500,000 and 1.5 million square miles of ocean, depending on how you draw the lines. That range alone tells you something. Even the boundaries of the mystery are not agreed upon. To search that much open water for wreckage is like trying to find a single lost coin somewhere in the state of Alaska. Except the coin may have sunk miles below the surface. The ocean floor in this region drops in places to more than 27,000 feet. That is deeper than Mount Everest is tall. A ship that sinks in those depths does not sit where rescue teams can easily reach it. It falls into a world of crushing pressure and total darkness, where the currents may carry debris far from where the vessel went down. Finding wreckage there is not simply difficult. In many cases, it may be practically impossible with the tools we have today. And so the ships remain missing, not because the ocean is necessarily hiding something strange, but because the ocean is simply vast and deep and old, and it does not give things back easily. Whether the losses in this particular stretch of water are truly unusual, or whether they reflect the ordinary, terrible mathematics of seafaring across centuries, is still a question researchers debate. Some say the numbers are not out of proportion when you account for the volume of traffic. Others say the pattern of complete disappearances, no wreckage, no signal, no survivors, is harder to explain away. For now, the docks are quiet. The water keeps moving, and somewhere far below the surface, the answers rest in the dark. Imagine floating just above the surface of the Atlantic on a clear, bright afternoon. The water below you is a deep, shifting blue, almost too blue, like something painted rather than real. The sun is high. The air is warm and still. There are no clouds on the horizon. From up here, everything looks calm. Everything looks safe. Now imagine that a plane flew through this same sky and never landed. That is the quiet strangeness at the heart of this section. Not storms, not fog, not the kind of weather that makes a pilot grip the controls and brace. Some of the most puzzling disappearances in the triangle happened on days that looked exactly like the one you are imagining right now. Clear skies, good visibility, experienced pilots, and then nothing. The most often cited example is a group of 5 Navy torpedo bombers that left a Florida air base in December of 1945. They were on a routine training flight. The pilots were not beginners. The weather at takeoff was described as fair. The planes flew out over the Atlantic and were never seen again. A rescue plane sent to search for them also vanished. No confirmed wreckage from any of the 6 aircraft was ever recovered. The official investigation concluded that the cause was unknown. That word, unknown, has sat in the record ever since. There are several theories about what happened that day. One idea is that the flight leader may have become disoriented over the open ocean, where the water and sky can blend together in ways that confuse even trained eyes. Without landmarks, distance and direction become very hard to judge. Some researchers believe the planes may have run out of fuel while searching for land in the wrong direction. The ocean would have taken them quickly after that. Another theory points to the instruments. Compasses in that region can behave strangely, and some researchers have wondered whether the navigational equipment gave the pilots false readings. If the instruments said one thing and the real world was something else, a pilot pilot might not know which to trust. That kind of confusion over open water with fuel running low could end very badly. But here is what makes the question harder to settle. Some aviation historians argue that the disappearance, while genuinely tragic and genuinely unexplained, was not as mysterious as it later became. They point out that the conditions that day were not as perfect as early accounts suggested. The weather worsened as the afternoon went on. The sea state was rough by the time the planes would have been low on fuel, and the area where they likely went down is deep and wide. Finding wreckage there, even today, would be extremely difficult. So the mystery has two layers. The first is what actually happened to those planes. The second is whether the story grew larger than the evidence over the decades that followed. Both questions remain genuinely open. Other aircraft losses in the triangle share this same texture. A commercial airliner disappeared in 1948 on a flight from the Azores to Bermuda. A British passenger plane vanished in 1949 on a similar route. In both cases, the weather was not severe. In both cases, no distress call was received. In both cases, the sea gave back very little. One theory that applies to some of these cases involves something called clear air turbulence. This is a sudden, violent shaking of an aircraft that happens with no visible warning. No clouds, no storm, nothing a pilot can see coming. It occurs when two bodies of air moving at different speeds collide invisibly. The triangle sits in a region where warm tropical air and cooler Atlantic air often meet. Some researchers have wondered whether unusually strong clear air turbulence could explain certain losses. Others say the turbulence in that region is not significantly different from other busy flight corridors in the world. That disagreement is itself part of the open question. Is the triangle genuinely different from other stretches of ocean? Or does it only seem that way because we have been paying closer attention to it for decades? From above, the water still looks the same. That deep, almost impossible blue. The surface catching the light in slow, rolling flashes. The horizon perfectly flat and perfectly still. A sky so clear you could see for 50 miles in any direction, and somewhere below that surface, or somewhere in that archive of old flight logs and incomplete reports, the answer to what happened on those clear days is still waiting. Patient and quiet, the way the ocean always is, holding what it knows without any sign of giving it back. Beneath the surface of the Atlantic, in the deep water below the Bermuda Triangle, the ocean floor holds something strange. It is not visible from a ship. You cannot see it from the air, but scientists have found it with instruments that measure pressure and temperature and the chemistry of the water itself. Down there, locked inside the cold sediment, are vast deposits of methane hydrate. Methane hydrate is a curious thing. It forms when methane gas, the same gas that burns in a kitchen stove, gets trapped inside a cage of frozen water molecules. The cold and the pressure of the deep sea hold it together. It looks almost like dirty ice. It sits quietly on the seafloor and in the sediment beneath it, stable as long as the conditions around it stay the same. But conditions do not always stay the same. Some researchers have wondered whether these deposits could, under the right circumstances, release their methane all at once. The idea is called the methane hydrate eruption hypothesis. The theory goes something like this. If the temperature of the deep water rises, or if the pressure changes, the frozen cage can break apart. The methane inside escapes as gas. It rises through the water in a great column of bubbles, churning and frothing upward toward the surface. The question that follows is a fascinating one. What would happen to a ship sitting above that column of rising gas? One line of thinking suggests it could be catastrophic. Water mixed with a large volume of gas becomes less dense. It loses its ability to hold a ship up. A vessel floating above such an eruption might, in theory, sink very quickly with little warning. The hull would not be crushed. The ship would simply lose its buoyancy, the way a ball loses air. It would go down fast, and it might leave very little behind. This idea has been explored in laboratory settings. Researchers have tested small models in tanks filled with bubbling water, and the results were striking enough to keep the question alive. Some scientists find the hypothesis genuinely plausible. The seafloor beneath the Bermuda Triangle does contain significant methane hydrate deposits, and that part is not disputed. But the hypothesis has serious critics, and their objections are worth sitting with. The main challenge is scale and timing. A methane eruption large enough to sink a ship would need to be enormous, and it would need to happen very suddenly. Geologists who study the seafloor point out that most methane releases in the deep ocean are slow and gradual. The gas seeps upward over long periods of time. A sudden, violent eruption of the kind the hypothesis requires is theoretically possible, but there is no confirmed modern record of one happening in this region with enough force to endanger a vessel. There is also the question of the aircraft. Methane rising through water cannot directly bring down a plane flying thousands of feet above the sea. Some versions of the theory suggest that a large enough eruption could release gas into the atmosphere, potentially affecting engine combustion, or even creating a brief zone of altered air density. But this remains deeply speculative. No controlled evidence supports it, and most aviation experts treat it with considerable skepticism. So, the methane hypothesis sits in an interesting place. It is not dismissed entirely. The geological conditions that would allow it exist in the region. The physics of buoyancy loss in gassy water are real and demonstrable on a small scale. But the leap from laboratory tank to open ocean, from small model to full-sized ship, from theory to confirmed event, is a large one. No wreck has ever been definitively linked to a methane eruption. No crew has ever reported seeing the telltale columns of bubbles before a disaster. What the ocean floor does tell us is that this part of the Atlantic is geologically active in ways that are still being mapped and understood. The sediment layers hold records of ancient events. Some of those events involved the release of enormous amounts of methane over geological time. Whether anything like that could happen on a human timescale, suddenly enough to matter to a ship or a plane, is a question that remains genuinely open. The deep water keeps its own record. It is written in pressure and chemistry, and the slow movement of sediment in a language that takes patient instruments and years of study to begin to read. cold dark beneath the triangle, the frozen methane waits, stable for now, quiet for now. What it might do, and whether it has ever done anything at all to the ships and planes that vanished above it, is something no one can say with certainty tonight. The ocean is never still. Even on the calmest day, when the surface looks like pale green glass, something is moving beneath it. Pressure is building. Water is shifting. Forces that take days or weeks to gather are quietly doing their work. The sea has rhythms, and some of those rhythms are very old and very large. One of the most discussed forces in the Bermuda Triangle is the rogue wave. A rogue wave is a single, enormous wall of water that rises far higher than the waves around it. It appears without much warning. It does not follow the pattern of the swells nearby. Sailors have described them for centuries, and for a long time, scientists were not sure they were real. They seemed too extreme, too sudden, too far outside what the math predicted. But in 1995, instruments on an oil platform off the coast of Norway recorded a wave nearly 26 meters tall rising out of relatively calm water. After that, the skepticism faded. Rogue waves are now understood to be real, though how often they form and exactly why is still being studied. One theory is that they occur when several wave trains, moving at slightly different speeds, arrive at the same point at the same moment. Their energies combine. The result is a single peak far taller than any of its parts. Another idea involves the way ocean currents can focus wave energy, bending and concentrating it the way a lens bends light. The Gulf Stream, which runs along the western edge of the Bermuda Triangle, is a strong and fast-moving current. Some researchers wonder whether it plays a role in creating the conditions where rogue waves are more likely to form. The question is genuinely open. For a ship, a rogue wave is not just dangerous. It can be catastrophic in a way that leaves almost no evidence. A large vessel struck by a wall of water that tall could sink in minutes. The hull could be breached before a distress signal is ever sent. The wreckage might scatter across miles of open ocean, and in deep water, much of it would simply sink and disappear. This is one reason some researchers find rogue waves a compelling explanation for certain triangle disappearances. The absence of debris, the sudden silence on the radio, the clear weather that surrounded the event, all of it fits the pattern of a rogue wave strike. But others are less convinced. They point out that rogue waves are not unique to the Bermuda Triangle. They have been recorded in the North Sea, in the waters off South Africa, in the Pacific. If rogue waves explain triangle losses, they should explain similar losses everywhere else too. And the statistical record, which will come up again later in this episode, does not clearly show that the triangle loses ships at a higher rate than other busy ocean regions. So the rogue wave theory may be part of the answer. Whether it is a special part of the triangle's answer is still uncertain. There are other hidden forces worth considering. The ocean breathes in cycles that last far longer than a single storm. Internal waves are one example. These are waves that move not on the surface, but deep inside the water column, along the boundary between layers of different temperature and density. They can be enormous, sometimes hundreds of meters tall from trough to crest, and they move slowly and silently far below anything a ship would notice. But they can push water upward in ways that affect surface conditions. They can alter the behavior of currents. Some researchers have wondered whether internal waves contribute to the unpredictable sea states sometimes reported in the triangle. The evidence is not conclusive. Tides, too, have their own long rhythms. The gravitational pull of the moon draws water in cycles that repeat roughly every 12 hours. But in certain shallow regions, tidal flows can become complex and irregular. The Bahama banks, which sit along the western edge of the triangle, are a vast shallow platform where tidal behavior is not always predictable. Water moves differently there than it does in open ocean. Currents can shift direction quickly. Sandbars appear and disappear. A navigator relying on charts that are even a few years old might find the bottom where the chart shows open water. All of these forces, the rogue waves, the internal waves, the tidal shifts, the focused energy of crossing currents, share something in common. They are cyclical. They build and release. They gather energy slowly and spend it quickly. They are not random chaos. They follow patterns, even if those patterns are too large and too slow for any one person to observe in a single crossing. The sea keeps its own time, and sometimes that time moves in ways we are only beginning to measure. There is a river in the ocean. That might sound like a strange thing to say. Rivers belong to land, to valleys and stones, and the slow pull of gravity toward lower ground. But the Gulf Stream is something very much like a river, and it moves through the Atlantic with a quiet, enormous power that most people never think about. The Gulf Stream begins in the warm waters of the Gulf of Mexico. It flows northward along the eastern coast of North America, then curves out into the open Atlantic, carrying warm blue water toward Europe. It is one of the strongest ocean currents on Earth. At its peak, it moves roughly 100 times more water than all the world's rivers combined. That number is hard to hold in the mind. 100 times. All the rivers, all at once. And the Bermuda Triangle sits right at its edge. The western boundary of the triangle runs close to the Florida coast, which is exactly where the Gulf Stream runs fastest and deepest. This is not a coincidence that researchers ignore. It is, in fact, one of the most discussed features of the region when people try to understand what might happen to a vessel that gets into trouble there. Here is the basic idea. A ship in distress, or a plane that goes down into the water, does not simply stay where it fell. The Gulf Stream moves at speeds of up to about 5 miles per hour in some stretches. That sounds slow, but over hours and days, a piece of wreckage, a life raft, a floating cushion, anything that enters the current can travel a very long distance from where it started. Search teams looking in the right area might find nothing, because the ocean has already carried everything away. Some researchers point to this as a straightforward explanation for why wreckage from certain disappearances was never found. The current took it. The search was in the right place, but the debris was already somewhere else. Others are not so sure. They point out that search and rescue teams in the modern era are well aware of the Gulf Stream. They account for drift their searches. And yet, some disappearances still produce no wreckage at all. So the current alone may not explain everything. It might explain some things. How much exactly remains an open question. The Gulf Stream also does something else that matters here. It creates a sharp boundary between water masses. On one side of the current, the water is warm and deep blue. On the other side, it is cooler and a different shade entirely. Where these two water masses meet, the conditions at the surface can become complicated. Winds behave differently. Fog can form quickly where warm and cool air meet above the water. Waves from different directions can cross and combine in ways that are hard to predict. This boundary effect is something oceanographers study carefully. Whether it contributes to the specific conditions inside the triangle is not settled. Some researchers think these boundary zones create pockets of unusual sea behavior. Others think the effect is modest and well within what sailors and pilots should be able to handle. There is also the question of what the Gulf Stream carries with it from below. The current does not just move surface water. It pulls deeper water along with it. And that deeper water can carry temperature differences, pressure changes, and even some researchers have wondered, pockets of gas rising from the seafloor. This connects back to the methane hydrate ideas from earlier. The question of whether gas rising through the water column might affect buoyancy, or even the air above the surface. The Gulf Stream's movement through this region could, in theory, stir things up in ways that are difficult to predict. Whether it actually does so in ways that matter for safety is something the science has not resolved. What is clear is that the Gulf Stream is not a passive backdrop. It is an active, powerful system. It shapes the weather above it. It moves the water around it. It carries heat from the tropics toward the north. It has been doing this for a very long time, long before any ship ever crossed the Atlantic, long before anyone drew a triangle on a map. The triangle does not exist in still water. It exists in the middle of one of the most dynamic ocean systems on the planet. The current flows through it, around it, along its edges. Whatever has happened in that region over the centuries, the Gulf Stream was always there, moving quietly, carrying things away, reshaping the surface of the sea. Whether that explains the mystery or only deepens it is something no one has fully answered yet. The ocean beneath the Bermuda Triangle holds some of the most extreme geography on Earth. This is not a gentle, shallow sea. In places, the water drops away into depths that are genuinely difficult to imagine. The Puerto Rico Trench, which lies along the northern edge of the Triangle's territory, reaches down to about 28,000 feet. That is roughly 5.5 miles of open water, pressing down into cold and total darkness. It is one of the deepest places in the entire Atlantic Ocean. To put that depth in some kind of human scale, consider this. If you placed the tallest mountain on land into that trench, its peak would still sit more than a mile below the surface. The water above it would be black and still and impossibly heavy. Very few things have ever gone down that far to look around. What lives down there, how the currents move, what the seafloor actually looks like in detail. Much of that remains genuinely unknown. The Triangle's geography is not only extreme in depth, it is also extreme in variety. Within a relatively short distance, the seafloor shifts from shallow coral banks, barely a few feet below the surface, to those crushing abyssal depths. The Bahamas sit on a platform of limestone so flat and pale it glows a soft turquoise from above. Then the bottom simply falls away, almost without warning, into the deep Atlantic basin. Sailors and pilots crossing this region move over an ocean that changes character completely beneath them. Even when the surface looks calm and ordinary, some researchers have pointed to this dramatic variation in underwater terrain as one possible reason why the Triangle has collected so many legends. A ship that founders in shallow water near the Bahamas might leave wreckage that washes ashore or gets spotted from above. But a ship that goes down over the deep basin or slides into the trench's outer reaches could vanish almost completely. The ocean at those depths swallows things quietly. There is no surface trace, no debris field that floats up in a recognizable pattern. It simply disappears. That disappearance, some suggest, is not supernatural. It may just be geography. Others point to the extreme speed of the Gulf Stream as another kind of record worth considering. In certain channels near the triangle, the Gulf Stream moves faster than almost any other ocean current on Earth. It can flow at 4 to 5 miles per hour in narrow passages, which sounds modest until you imagine a disabled vessel caught in it. Any debris, any floating remnant of a lost ship or aircraft would be carried hundreds of miles away from the site of the accident within days. By the time a search begins, the evidence is already somewhere else entirely. This is one of the more straightforward theories offered by oceanographers, and it does not require anything unusual to explain the lack of wreckage. The triangle is also home to some of the most intense and sudden storm systems in the Atlantic basin. Waterspouts, those spinning columns of water and air that rise from the sea surface, form here with notable frequency. A large waterspout can reach heights of several thousand feet. It can generate winds strong enough to damage a vessel or disorient a small aircraft. They form quickly, sometimes in clear conditions, and they can be difficult to see on radar or spot from a distance until a ship is very close. One theory holds that waterspouts account for some of the more puzzling losses, particularly those that happened in otherwise fair weather. But this remains a theory. There is no confirmed record linking a specific disappearance directly to a waterspout. Then there are the blue holes. These are underwater caves and sinkholes, some of extraordinary size, scattered across the shallow seafloor of the Bahamas. The Great Blue Hole off the coast of Belize is perhaps the most famous example in the wider region. A circular sinkhole nearly 1,000 feet across and over 400 feet deep, dropping straight down through ancient limestone. The Bahamas contain dozens of similar formations, some of them mapped, many of them not. What lies inside the unmapped ones, how far they extend, whether they connect to deeper systems, these are genuinely open questions. Some researchers wonder whether the unusual water movement around these formations could affect small vessels in shallow areas. Others consider that idea speculative at best. What is clear is that the triangle sits over some of the most varied and extreme underwater terrain on the planet. The depths are real. The currents are real. The storms are real. Whether any of these extremes, alone or together, explain the region's reputation is a question that remains open. The ocean keeps its records quietly, and it does not always share them. Somewhere beneath the surface of the Atlantic, in the wide blue space between Florida and the islands, the ocean floor holds its own quiet record. It does not speak. It does not move quickly. But over thousands of years, it has gathered things, layers of sediment, ancient shells, the slow drift of particles from the water above, and it keeps them in a kind of stillness that the surface world never knows. The floor of the Bermuda Triangle is not one single thing. It shifts and changes as you move across it. Near the coast of Florida, the seafloor is relatively shallow, a broad shelf of pale limestone and sand. But move eastward, and the bottom drops away. The water deepens slowly at first, then more steeply, until you reach places where the ocean is more than 5 miles deep. That is a depth so great that the pressure down there would crush most things we build. The darkness is total. The cold is immense. One of the quieter details about this region is the texture of the sediment on the floor. In shallower areas, the sand is made partly of tiny fragments of coral and shell. Under a microscope, each grain has its own shape, curved edges, small holes, the ghost of a living thing that once filtered the warm Caribbean water. These grains are called biogenic sediment, meaning they came from life. They are the remains of creatures so small that a single handful of sand might hold millions of them. Deeper down, the sediment changes. The grains become finer, softer, almost like powder. Scientists call this deep-sea ooze, and it is made mostly of the shells of microscopic organisms that drifted down from the surface over millions of years. Some of these shells are made of calcium carbonate, the same material as chalk. Others are made of silica, the same substance as glass. When you look at them under a microscope, they look like tiny sculptures. Spirals, stars, hollow spheres with delicate lattice walls. Each one is the remains of a creature that lived and died in the sunlit water far above. here is something that researchers find genuinely puzzling. In some parts of the Atlantic floor near this region, the sediment record shows layers that do not quite match what we would expect. There are bands of material that suggest past disturbances, events that stirred the bottom and mixed the layers together. What caused those disturbances is not always clear. Some researchers point to ancient underwater landslides, where the edge of the continental shelf gave way and sent sediment rushing down into the deep. Others suggest that large releases of gas from the seafloor could have churned the sediment from below. The record is there, but the cause remains open. The floor also holds features that are easy to miss on a map, but remarkable up close. There are long, low ridges of hardened carbonate rock that formed when ancient reefs were slowly buried and compressed. There are flat plains of abyssal sediment, so smooth and undisturbed that they look almost artificial. And there are places where the rock itself is fractured, where old faults in the crust have left cracks and steps in the seafloor that drop away suddenly into shadow. What lies on the floor in terms of human history is another quiet question. Ships that were lost in this region over the past few centuries would, in theory, still be somewhere on the bottom. The ocean preserves metal and wood differently depending on depth, temperature, and the chemistry of the water. In shallow water, wood rots quickly and iron rusts. In the deep cold, things can last much longer. Some wrecks have been found. Many have not. The ocean floor in this region has not been fully mapped at high resolution. Large sections of it remain, in a practical sense, unseen. That is a fact that tends to surprise people. We have better maps of the surface of the moon than we do of parts of the Atlantic floor. The technology to scan the deep seafloor in fine detail is expensive and slow. Survey ships must move carefully, sending sound pulses down and waiting for the echo. It takes time, and the triangle's floor, with its mix of shallow banks and deep basins, is a complicated place to map. So the floor holds its silence. It holds the fine powder of ancient shells. It holds the fractured rock of old faults. It holds, perhaps, the remains of things that vanished from the surface and were never explained. What exactly is down there in all of it is still being learned. The picture is incomplete, and in that incompleteness, there is something worth sitting with quietly in the dark before sleep comes. There is a particular kind of cloud that forms over warm ocean water. It does not look like the soft, rounded clouds you might see drifting over a meadow on a summer afternoon. This kind of cloud is different. It sits low and flat, almost like a lid pressed down over the sea. Sailors have noticed these clouds for centuries, long before anyone had a name for what they were or a theory to explain them. Over the waters of the Bermuda Triangle, certain cloud formations have drawn attention for a long time. Pilots flying over the region in the mid-20th century sometimes reported strange, hexagonal clouds shaped roughly like six-sided figures, sitting in clusters over the open Atlantic. These were not the kinds of clouds most pilots had seen before. They were wide and flat on the bottom, with sharp, almost geometric edges. Some pilots noted them in their logs. Others simply flew on and said nothing. For a long time, no one paid those notes much attention. The clouds were unusual, but the sky is full of unusual things, and pilots have a great deal to focus on without stopping to wonder about the shape of a cloud. Then, years later, a small group of atmospheric researchers began looking at satellite images of the region. They noticed something in those images that matched what the old pilots had described: hexagonal cloud patterns, some of them stretching across 50 to 90 miles of open ocean. The researchers wondered what those shapes might mean. One idea that emerged was that these clouds could be connected to something called air bombs. Powerful downdrafts of cold air that drop suddenly from the base of a cloud and hit the ocean's surface at very high speed. Some estimates suggested these blasts of air could reach speeds of over 100 miles per hour when they struck the water. If that theory holds, the implications are significant. A sudden wall of air moving that fast across the surface of the ocean could create waves of enormous size in a very short time. Not the slow, rolling swells that build over days of open sea travel, but sharp, steep waves that rise quickly and hit a vessel from multiple directions at once. A ship caught in that kind of sea would have very little warning. The water would seem calm, and then it would not be. But this theory is far from settled. Other atmospheric scientists have pushed back on it. They point out that hexagonal clouds are not unique to the Bermuda Triangle. They form in many parts of the world where warm ocean water meets cooler air above. The geometry of the cloud, they argue, does not by itself tell us anything special about what happens beneath it. The air bomb idea is interesting, they say, but the evidence connecting those specific cloud formations to specific losses in the triangle is thin. This is where the history of discovery gets complicated. Humans have been observing the sky over this part of the ocean for a long time, but the tools for understanding what they saw came slowly. Early sailors had no way to measure wind speed at altitude, no way to track the movement of air masses from above, no way to know what was happening in the atmosphere 1,000 feet over their heads. They could only feel what reached them at sea level. The instruments came gradually. Barometers to measure air pressure, anemometers to measure wind. Eventually, weather balloons that could carry sensors up into the sky and radio their readings back down. And then, much later, satellites that could photograph cloud patterns across hundreds of miles of ocean in a single image. Each new tool revealed something the previous one had missed, and each new revelation raised new questions. The atmosphere over the western Atlantic is not simple. Warm air rises from the Gulf Stream below. Cold air pushes down from the north. Tropical systems form and dissolve. The air itself is in constant, slow motion, and the patterns it makes are still not fully understood. Some researchers believe that atmospheric conditions over the triangle are genuinely unusual, not supernatural, but complex in ways that can catch even experienced pilots and sailors off guard. Others believe the region is no more complex than any other stretch of open ocean at similar latitudes. The clouds are still there. Satellites still photograph them. Researchers still argue about what they mean. The atmosphere keeps its own record, written in shapes and pressures and temperatures that humans are only beginning to read with any confidence. What those hexagonal clouds are truly telling us, if anything at all, remains an open question drifting quietly above the blue water. There is a theory about the Bermuda Triangle that surprises many people when they first hear it. It does not involve strange magnetic forces or sudden walls of water rising from the deep. It does not require any unusual property of the ocean at all. The theory is simply this: that human beings, doing their best in difficult conditions, sometimes make mistakes, and that those mistakes, in a busy and demanding stretch of ocean, can be enough. This idea feels almost too plain. After decades of stories about vanishing ships and silent cockpits, the suggestion that ordinary human error might explain a large portion of the losses seems almost disappointing. But some researchers who have studied the triangle's history carefully say that the disappointment itself is part of the puzzle. We expect a grand cause. We look for something extraordinary, and in doing so, we sometimes overlook the quiet, unglamorous explanations sitting right in front of us. The waters between Florida, Bermuda, and Puerto Rico are among the most heavily traveled in the world. Thousands of vessels cross that stretch of ocean every year. Pleasure boats, cargo ships, small private planes, and commercial aircraft all move through the same region. When you have that much traffic, you also have a higher chance of something going wrong. More boats in the water means more chances for a navigation mistake, a mechanical failure, or a moment of poor judgment in bad weather. Some researchers point out that the triangle sits at the edge of a region where weather can change with very little warning. Afternoon thunderstorms build quickly over warm water. Visibility can drop from clear blue sky to near zero in a matter of minutes. A small boat caught in one of those storms, far from shore, and without modern navigation equipment, faces real danger. And for much of the 20th century, the vessels that crossed this region did not have the tools that sailors carry today. No GPS, no satellite weather updates, no automatic distress beacons that ping a rescue station the moment a hull goes under. The story of Flight 19 is often told as evidence of something deeply strange. 5 Navy torpedo bombers flew out over the Atlantic in December 1945 and never came back. The lead pilot's radio transmissions described confusion about his position. He seemed uncertain which direction was east and which was west. Some accounts of that day suggest the compasses were behaving oddly, but other researchers, looking at the same records, suggest a different reading. They point to evidence that the flight leader may have made a navigational error early in the mission, and that the confusion that followed was the result of that first mistake compounding over time. The planes ran out of fuel over open water. The night was dark. The sea was rough. None of that requires a supernatural explanation. This is where the counterintuitive part comes in. We tend to assume that trained professionals, using good equipment in a region they know well, should not get lost. But the ocean is vast and featureless in a way that land is not. There are no landmarks. There are no road signs. On a cloudy night, with no stars visible and no coast in sight, even an experienced navigator can become uncertain. That uncertainty, if it goes uncorrected, can grow. Some aviation researchers use the phrase spatial disorientation to describe what happens when a pilot loses track of which way is up. The inner ear sends signals to the brain that feel completely real, but are wrong. A plane can be banking steeply, while the pilot feels perfectly level, without instruments to check against. The body's own senses become unreliable guides. This is not a failure of courage or skill. It is simply a limit of human biology, and it can happen anywhere, not just in the triangle. The competing view, of course, is that human error alone cannot account for every disappearance. Some researchers argue that the sheer number of incidents, spread across many decades and involving many different kinds of vessels and aircraft, suggests something more than a run of bad luck and poor decisions. They point to cases where experienced crews with good equipment vanished without sending a distress signal, without leaving wreckage, without any trace at all. Those cases, they say, deserve a harder look. And so the question stays open. Human error is real. It is common. It is probably responsible for more losses in the triangle than any single unusual force. But whether it explains all of them, or even most of them, is something researchers still debate. The ocean does not give up its answers easily, and the gap between what we can explain and what we cannot is still quietly there. Beneath the surface of the ocean, the earth is not still. It breathes in a way. It shifts. Deep below the seafloor, vast rivers of molten rock move through the mantle, that thick, slow layer of hot stone sitting between the thin crust we live on and the iron core far below. This movement is almost impossibly slow, but over millions of years, it reshapes everything. And one of the things it shapes, quietly and continuously, is the planet's magnetic field. The magnetic field is the invisible force that makes a compass needle point north. It wraps around the entire Earth like a soft shell, generated deep inside the planet by the churning of liquid iron in the outer core. Most of the time, it is steady enough to trust. Sailors have relied on it for centuries, but it is not perfectly uniform. In some places, the field is slightly stronger or slightly weaker. In some places, it pulls a compass needle just a little off true north. These variations are called magnetic anomalies, and they exist all over the world. The Bermuda Triangle sits in a region where the seafloor has a complicated history. The Atlantic Ocean floor here was shaped by ancient volcanic activity, by the slow spreading of tectonic plates, the enormous slabs of rock that make up the Earth's crust, and by layers of sediment that have built up over tens of millions of years. Some researchers have wondered whether the particular geology of this region creates unusual magnetic conditions, whether the rocks beneath the water, with their specific mineral content and their volcanic past, might cause local variations in the magnetic field strong enough to affect navigation. It is a reasonable question. Certain types of rock, especially those rich in iron-bearing minerals, can produce measurable magnetic anomalies. Volcanic rock in particular tends to carry a magnetic signature, frozen in place at the moment the rock cooled from lava. If enough of that rock sits close to the surface of the seafloor, it could, in theory, create a zone where compass readings drift slightly from what a navigator expects. But here, is where the picture becomes less clear. Most modern researchers who have studied the magnetic data for the Bermuda Triangle region have not found evidence of anomalies dramatic enough to explain large-scale navigational failures. The variations that exist are real, but they appear to be modest. Comparable anomalies exist in many other parts of the world's oceans, and ships and planes navigate them without incident every day. So the question becomes whether the magnetic irregularities in this region are genuinely unusual, or whether they fall within the normal range of variation found across the Atlantic. Some researchers take a different view. They point out that even small, consistent errors in compass readings can compound over time. A navigator who trusts a compass that is off by just a few degrees will drift further and further from the intended course over a long voyage, especially in poor visibility or rough weather. That drift could matter enormously. The sea is vast. A ship that is even slightly off course in the wrong conditions might never find the harbor it was looking for. There is also a subtler connection worth sitting with. The Earth's magnetic field is not fixed forever. Over geological time, it wanders. The magnetic poles shift slowly, and the field itself fluctuates in strength. There have been periods in Earth's deep past when the field weakened significantly before reversing entirely. A process called geomagnetic reversal, where north and south magnetic poles essentially swap. We are not in such a period now, but scientists do observe that the field has been gradually weakening over the past few centuries. Whether that slow, global weakening has any meaningful effect on navigation in specific regions like the Bermuda Triangle is, at this point, an open question. What ties all of this together is the idea that the Earth below the ocean is not a passive backdrop. It is an active system. The rocks carry magnetic memory. The seafloor spreads and shifts. The mantle moves. The core churns. All of these processes connect to the thin layer of water and air at the surface where ships sail and planes fly. The connections are real, even if their precise effects in any one place are hard to measure. Whether those connections are strong enough or strange enough to explain what has happened in the Bermuda Triangle remains genuinely uncertain. The magnetic story is one thread among many. It does not resolve the mystery. It deepens it in a quiet way by reminding us how many invisible forces are always at work beneath the surface of the world we think we know. Beneath the shallow turquoise waters of the Bahamas, there are holes in the ocean floor, not small ones. Some of these openings drop straight down for hundreds of feet, their walls dark and smooth, their bottoms hidden in a cold that sunlight never reaches. From above, they look like deep blue circles pressed into the pale sandy seafloor. Locals have called them blue holes for as long as anyone can remember. Scientists have been studying them for decades, and the more they look, the more questions they find waiting at the bottom. A blue hole is, at its simplest, a submerged cave or sinkhole. It formed long ago, during a time when sea levels were much lower than they are today. Back then, rainwater soaked into the limestone rock of what is now the seafloor. That water was slightly acidic, the way rainwater naturally is. And over thousands of years, it slowly dissolved the rock from the inside. Chambers formed, tunnels formed. Then the sea level rose, as it has done many times across Earth's long history, and the ocean flooded those ancient hollow spaces. The result is what we see now: dark, circular openings in a bright, shallow sea. The Bahamas sit at the edge of the Bermuda Triangle's southwestern corner. The blue holes here are among the most studied in the world, and they are genuinely unusual places. The water inside them behaves differently from the water around them. Near the surface, a blue hole might hold warm, oxygen-rich seawater, but deeper down, the layers change. Oxygen disappears. The water becomes still and cold. Some blue holes contain a layer of hydrogen sulfide, a gas that forms when organic matter breaks down without oxygen. That layer looks almost like a thin cloud suspended in the water column. It marks the boundary between the living upper world and the airless world below. What lives in these places and what has been preserved in them is still being discovered. Because the deep water in a blue hole barely moves, things that sink into it tend to stay. Researchers have pulled up bones, shells, and plant material that have been sitting undisturbed for thousands of years. One blue hole off the coast of Andros Island in the Bahamas, known as Sawmill Sink, has yielded the remains of animals that lived during the last ice age. Tortoises, crocodiles, birds, all preserved in the still, airless dark. The sediment layers inside blue holes act like a slow record of past climates, each layer a page in a very old book. Some researchers wonder whether blue holes might hold clues about the kinds of conditions that exist in the triangle more broadly. The seafloor in this region is not flat and featureless. It is riddled with old geology, with limestone shelves and sudden drop-offs and underwater formations that were shaped by forces operating over millions of years. Whether any of that geology contributes to the unusual conditions sometimes reported in the triangle is an open question. One idea is that the same processes that carved the blue holes, water moving through porous rock, gases accumulating in sealed chambers, might still be active in smaller, less visible ways across the wider seafloor. Another view is that the blue holes are simply fascinating geological features with no special connection to the triangle's reputation at all. The blue holes are also changing, though very slowly, as sea levels continue to rise. The conditions inside them shift. The chemistry of the water changes. The layers of sediment keep building up, burying older records deeper. Scientists are working to study these places before those records become harder to reach. Some of the most detailed surveys have only happened in the last few years. Using equipment that can map the walls and floors of these holes with a precision that was not possible before. Each survey tends to reveal something unexpected. There is a particular quality to the image of a blue hole that is hard to shake. You are floating in warm, clear, sunlit water. The sandy floor is visible beneath you, pale and bright. And then, without much warning, the floor simply opens. The color shifts from pale green to deep blue to something closer to black. The edge of the hole is sharp and clean. Below it, there is only depth. You cannot see the bottom. You do not know exactly what is down there. The hole has been there for thousands of years, patient and still, while the sea moved above it and the world changed around it. patience is something the blue holes share with the larger mystery they sit inside. The triangle has been studied, argued over, and mapped for decades. And still, in places like these, the ocean keeps its quiet. Beneath the surface of the Bermuda Triangle, the ocean floor is not flat. It is not smooth. It is one of the most varied and dramatic pieces of underwater geography on Earth, and much of it has never been seen by human eyes. Close to shore, the water is shallow and bright. The Bahama banks, those wide, pale platforms of limestone that sit just under the surface, glow a soft turquoise in daylight. From above, they look almost like light itself, scattered and shimmering. A pilot flying over them on a clear day would see the bottom easily. The sandy floor lit up in pale greens and blues. The water there is warm and calm and full of color. But the banks end. And when they end suddenly. Just east of the Bahamas, the seafloor drops away into something called the tongue of the ocean. This is a deep, narrow channel that plunges to around 6,000 feet. From the air, the color change is visible. The pale turquoise goes dark almost instantly, shifting to a deep, cold blue that borders on black. That color change is not just beautiful, it marks the edge of a world that light can barely reach. This is one of the things that makes the geography of the triangle so unusual. Within a very short distance, you can go from water that is 50 feet deep to water that is over a mile deep. Ships and planes that go down in shallow water are often found. Ships and planes that go down in deep water are often not. The ocean simply swallows them, and the darkness keeps them. The Puerto Rico Trench lies to the southeast of the triangle's boundaries. It is the deepest point in the Atlantic Ocean, reaching down to about 28,000 feet in some places. That is deeper than Mount Everest is tall. Light does not reach the bottom of the Puerto Rico Trench. No sunlight has ever touched it. Down there, the pressure is enormous. The temperature is just above freezing, and the darkness is total and absolute. Some researchers have wondered whether the proximity of such extreme depths plays a role in why some disappearances in this region are never solved, not because of anything mysterious about the trench itself, but simply because of physics. A vessel that sinks into water that deep leaves almost nothing behind. Debris scatters, currents carry it. The sheer weight of miles of water above crushes and compresses. Evidence disappears not by magic, but by depth. Others point out that many of the famous disappearances happened in relatively shallow water, not over the trench at all. Flight 19, the group of Navy planes lost in 1945, was flying over the shallow waters near Florida and the Bahamas. If the planes went down there, the seafloor should have been reachable. The fact that so little was found in those shallower areas is, to some researchers, the more puzzling part of the story. Light behaves strangely over warm tropical water, too. The surface of the ocean in this region can act almost like a mirror in certain conditions. When warm, moist air sits just above cooler water, light bends. It curves. Distant objects appear to float above the horizon. Nearby objects seem to vanish. This effect, sometimes called a fata morgana, a kind of mirage that bends light across long distances, has been documented in warm ocean environments around the world. Whether it has ever contributed to a navigational error in the triangle is unknown. But the physics that allows it to happen are real and well documented. There is also the question of what light reveals on the ocean floor when researchers do manage to look. Sonar surveys of the seafloor in and around the triangle have found ancient riverbeds carved out when sea levels were much lower thousands of years ago. They have found coral formations, underwater cliffs, and long ridges of rock. They have not found anything that explains the disappearances, but they have also not finished looking. The surveys are incomplete. Large sections of the seafloor here remain unmapped at high resolution. The ocean holds its geography close. It does not offer its secrets easily. The light that dances on the surface of the Bahama banks, that brilliant, almost luminous turquoise, tells one story. The darkness at the bottom of the Puerto Rico Trench tells another. Between those two extremes lies a vast middle world of shifting depth and changing pressure, where the light fades gradually and then disappears entirely. What rests in that middle world, in those unnamed valleys, and uncharted ridges is still largely unknown. The geography is real. The depths are real. What they may or may not be hiding remains, for now, an open question. There is a sound that old sailors described when they crossed certain stretches of open water. Not a roar, not a crash, something quieter. A low, steady hum beneath the hull, or a strange silence where there should have been wind. They wrote it down in their logs. They told the story when they reached port, and those stories passed from mouth to mouth across centuries, became something larger than any single voyage. The history of disappearance stories in the Bermuda Triangle is in many ways a history of how human beings make sense of loss at sea. Ships have always vanished. The ocean is vast and deep and indifferent to the small wooden or iron things that move across its surface. But some disappearances felt different. Some left no wreckage, no bodies, no clear explanation. And those are the ones that stayed in people's minds long before anyone called it the Bermuda Triangle. Sailors in the Caribbean and the Western Atlantic spoke of waters that behaved strangely. Christopher Columbus, crossing this region in 1492, wrote in his journal about a flame that appeared to fall from the sky into the sea, and about compass needles that did not point where they should. Historians have offered many explanations for those entries. Some suggest the flame was a meteor. Some suggest the compass variation he noticed was simply the natural difference between magnetic north and true north, which is well documented in that part of the ocean. Others note that Columbus may have been writing with a certain drama in mind, knowing his journals might one day be read by powerful people. The true meaning of what he recorded remains open. The stories grew louder in the 19th century. Ships disappeared in the region with some regularity, as they did in every busy stretch of ocean, but a few cases gathered particular weight. The Mary Celeste, found drifting and abandoned in 1872, is often placed in the Triangle story, though it was actually discovered much further east, near the Azores. The association stuck anyway. That is part of how the legend works. A strange story from anywhere in the Atlantic can find its way into the Triangle's account, pulled in like debris by a slow current. The 20th century gave the story its loudest chapters. Flight 19, the 5 Navy bombers that vanished in December of 1945, became the defining moment. The pilots reported confusion about their position. Radio contact grew fragmented and then stopped. A rescue aircraft sent to find them also disappeared. No confirmed wreckage from Flight 19 was ever recovered. That single event, more than any other, planted the triangle firmly in the public imagination. Some researchers point to instrument failure, disorientation, and the difficult weather conditions of that afternoon. Others note that the area where the planes likely went down is deep and heavily trafficked by strong currents, which could scatter wreckage quickly. The question of exactly what happened that day has never been fully closed. What followed was a kind of echo. Once the triangle had a name and a reputation, older stories were re-examined through its lens. Disappearances that had been recorded and filed away were pulled back out and reconsidered. Some were genuine mysteries. Some had explanations that had simply been forgotten or overlooked. The sound of the legend grew louder with each retelling, and it became harder to separate the original event from the story that had grown around it. One researcher, Lawrence David Cush, spent years in the 1970s going back to original sources. He looked at weather records, insurance reports, and the actual dates and locations of the incidents most often cited. He found that many of the disappearances had occurred outside the triangle's boundaries, or during storms that were not mentioned in popular accounts, or had explanations that were simply left out of the retelling. His conclusion was that the triangle's reputation was, at least in part, a product of selective storytelling. But other researchers pushed back. They argued that even accounting for those corrections, certain cases remained genuinely unexplained. That tension has never been resolved. The history of disappearance stories in this region is also a history of how we tell stories about the unknown. We reach for patterns. We look for a single cause. We want the ocean to have a reason for what it takes. And when no reason appears, the silence left behind becomes its own kind of sound. That low hum beneath the hull. That stillness where the wind should be. Sailors have always listened for it, and the question of what it means, if it means anything at all, drifts on through the years, quiet and unanswered, like a ship moving slowly into open water with no one watching from the shore. There is something quietly clarifying about numbers, not the dramatic kind of numbers, not the ones that shout or alarm, the quiet kind, the kind that sit in ledgers and logs, recorded by careful hands over many decades, and simply tell you what happened. Lloyd's of London is one of the oldest insurance markets in the world. For centuries, it has tracked ships and their fates. It assigns risk. It calculates loss. It does this with no interest in legend or story. It only cares about what the records show. And what Lloyd's has said more than once about the Bermuda Triangle is worth sitting with for a moment. The rates they charge for ships passing through that region are not elevated. They are not higher than rates for other busy stretches of open ocean. That is a quiet but significant thing. Insurance markets are not sentimental. They do not give discounts to dangerous places. If the triangle were statistically swallowing ships at an unusual rate, the numbers would show it. The premiums would reflect it. And yet, they do not. The United States Coast Guard has said something similar when researchers have asked them directly about the Bermuda Triangle. The Coast Guard has pointed to their own records. Those records do not show an unusual number of incidents in that region compared to other heavily traveled ocean corridors. The Atlantic is a busy place. Ships and planes move through it constantly. Losses happen across the whole ocean, not clustered in one triangular patch of water. Some researchers have gone further and looked at the raw counts. One careful analysis, done in the 1970s by a researcher named Lawrence David Cush, went back through the original reports of ships and planes said to have vanished in the triangle. He found something unexpected. Several of the incidents had taken place outside the triangle's boundaries entirely. Some had occurred in storms that were well documented at the time, but left out of later retellings. A few had simply been reported incorrectly, with dates or locations that didn't match the original sources. Cush's conclusion was direct. He argued that the mystery of the Bermuda Triangle was, in large part, a manufactured one, built from selective storytelling, missing context, and the natural human tendency to find patterns where none exist. His view is not universally accepted. Some researchers push back and say his analysis was itself too selective. The debate over his methods continues quietly in the background of this whole conversation. But even setting Cush aside, the broader statistical picture is worth holding in your mind. The Bermuda Triangle sits at the intersection of some of the world's busiest shipping and aviation routes. More traffic means more opportunity for things to go wrong. A region with 10 times the traffic might naturally produce 10 times the incidents without being any more dangerous per mile traveled. Comparing raw numbers without accounting for traffic volume can make a busy place look cursed when it is simply busy. There is also the question of what gets counted. The triangle's boundaries have never been officially defined. Different writers draw the shape differently. Some include Bermuda, Miami, and Puerto Rico as the 3 points. Others stretch it further. When the boundaries shift, the incidents inside them shift too. A disappearance that falls outside one version of the triangle can fall inside another. This flexibility makes the statistics hard to pin down in any rigorous way. And yet, something keeps people coming back to this question. The numbers may not support a special danger. The insurance markets may not see unusual risk, but the stories persist. The names of ships and planes still surface in conversation decades later. Flight 19, the USS Cyclops, the Marine Sulphur Queen. These are real losses, real people, real mysteries that were never fully explained. The statistics say the region is not anomalous. The individual cases say something happened that we still don't entirely understand. Both things can be true at once. A place can be statistically ordinary and still contain events that resist clean explanation. The math doesn't erase the mystery. It just changes its shape. Instead of asking why the triangle is dangerous, the question becomes something quieter and perhaps more interesting. Why do certain losses in certain places lodge themselves so deeply in human memory? What is it about an open ocean and an unanswered question that the mind returns to again and again, long after the ledgers have been closed? The numbers offer one kind of answer. They say, "This place is not special." But the stories offer another kind of answer entirely. And the two answers have not yet found a way to fully agree. By now, many theories have gathered around the Bermuda Triangle like ships anchored in a quiet harbor. Each one offers something. Each one also leaves something unexplained. And when you lay them side by side, what you notice most is how none of them quite closes the question on its own. Start with the methane hypothesis. Deep beneath the seafloor of the Western Atlantic, pockets of frozen gas sit locked inside the sediment. Some researchers believe that if enough of that gas releases at once, it could rise through the water in a great churning column of bubbles. A ship caught above such a release might lose buoyancy very quickly. The water would become less dense, less able to hold weight. The vessel could sink before a distress signal was ever sent. It is a striking idea, and some laboratory experiments have supported parts of it. But other researchers point out that no confirmed methane eruption has ever been directly linked to a documented disappearance in the triangle. The seafloor in that region does contain gas hydrates, frozen compounds of methane and water. But whether they release in ways large enough and sudden enough to sink ships remains genuinely uncertain. Then there is the rogue wave theory. The ocean is not a flat, predictable surface. Waves can combine in unexpected ways, stacking on top of one another to form walls of water far taller than the surrounding sea. These rogue waves, sometimes called freak waves, were once considered sailors' myth. But ocean sensors and satellite data have since confirmed they are real. A wave of that size could overwhelm a vessel without warning, leaving no wreckage and no time to call for help. The triangle sits where the Gulf Stream, deep Atlantic swells, and storm systems from multiple directions can all meet. Some researchers think this makes the area more prone to such events. Others note that rogue waves have been recorded all over the world's oceans, and that the triangle has no clear statistical edge over other busy shipping corridors. Magnetic anomalies offer another thread. The Earth's magnetic field is not perfectly uniform. It shifts and dips in ways that vary by location. Some researchers have suggested that unusual magnetic behavior in parts of the triangle could cause compass readings to drift without a navigator realizing it. A small, steady error in heading, held over many hours, could carry a ship or plane far from its intended course. This idea has a long history in triangle lore, but careful surveys of the region's magnetic field have not found anything dramatically different from other parts of the Atlantic. The anomalies that exist are real but modest. Whether they are enough to explain disappearances, or whether they simply add a small layer of difficulty to an already challenging environment, is still an open question. Human error and the limits of older technology sit at the center of a very different kind of explanation. Many researchers who have studied the triangle's history argue that the disappearances, when examined one by one, often have mundane explanations. Navigational mistakes, sudden storms, equipment failures, overloaded vessels, pilots flying into instrument conditions without proper training. The triangle covers a region of heavy traffic, unpredictable weather, and warm, fast-moving water that can carry wreckage far from where a vessel went down. Under those conditions, some researchers argue, the number of losses is not surprising at all. The mystery, by this view, is partly a product of how the stories were collected and retold, rather than a product of the ocean itself. And yet, that explanation does not fully satisfy everyone either. Some researchers point to cases where the circumstances remain genuinely hard to explain. Experienced crews, clear weather, no distress call, no wreckage. These cases are fewer than the popular story suggests, but they exist, and they sit at the edge of what the ordinary explanations can reach. What makes the triangle so persistent as a question is exactly this. No single theory accounts for everything. The methane idea is striking, but unconfirmed. The rogue wave idea is plausible, but not unique to the region. The magnetic anomaly idea is real, but modest. The human error idea is probably correct for many cases, but may not cover all of them. Each theory illuminates one corner of the picture. The rest stays in shadow. The ocean does not offer easy answers. It is deep and wide, and it keeps what it takes. The triangle is a place where several difficult forces overlap, and where the record of what happened is often incomplete, whether that overlap adds up to something genuinely unusual, or whether it simply looks that way from a certain angle, is a question the sea has not yet answered. There is something quietly remarkable about a place that has been studied for decades and still holds its secrets close. The Bermuda Triangle has drawn researchers, oceanographers, meteorologists, and marine scientists for generations. And yet, even now, even with satellites overhead and sensors beneath the waves, the region gives up its answers slowly. Some questions remain open in ways that are genuinely surprising. Not because the science is poor, but because the ocean itself is vast, and the atmosphere above it is complicated, and the floor beneath it is still largely unmapped. One of the most active areas of current research involves the ocean floor itself. Large portions of the seafloor beneath the Western Atlantic, including the areas that fall within the triangle, have never been surveyed in high detail. Scientists use sonar, a tool that sends sound waves downward and listens for the echo, to build pictures of the bottom. But full, fine-grained surveys take enormous time and resources. What lies in the deeper trenches and valleys of this region is still, in many places, genuinely unknown. Some researchers believe that detailed mapping could reveal geological features that help explain unusual water behavior at the surface. Others are less certain that the floor holds any special answers. The debate stays open. The methane hydrate question is still being studied, too. Methane hydrates are frozen deposits of gas locked inside ice-like crystals on the ocean floor. Some scientists have proposed that when these deposits break apart, they release large bubbles of gas that could affect buoyancy, the ability of a ship to float. Laboratory experiments have shown that large gas releases can, under certain conditions, reduce the density of water enough to sink objects, But whether this happens in the Bermuda Triangle region, at the scale needed to explain ship losses, is still a matter of active inquiry. Other researchers point out that the conditions required for a catastrophic release are very specific, and that the evidence for such events in this region remains thin. The question is genuinely unresolved. Atmospheric science is another area where the work continues. The hexagonal cloud formations spotted by satellite over this part of the Atlantic have attracted real scientific attention in recent years. Some meteorologists believe these unusual cloud shapes may be linked to powerful air bursts, sudden downward blasts of wind that could create dangerous conditions at sea level. Others argue that hexagonal clouds are not unique to this region, and that drawing a connection to disappearances is premature. The research is ongoing, and no firm conclusion has been reached. Ocean current modeling is also growing more sophisticated. The Gulf Stream, that wide, vast river of warm water moving through the Atlantic, behaves in ways that scientists are still refining their understanding of. Its edges can produce eddies, which are circular currents that spin off from the main flow. These eddies can move debris, shift the paths of floating objects, and create localized zones of unusual water behavior. Whether eddies in this region have played a role in past incidents is something that better current modeling may eventually help answer, or may not. The models are improving, but the ocean is large. Rogue wave science has advanced considerably in recent decades. Rogue waves, single, unusually tall waves that appear without warning, were once considered sailors' legend. Now they are accepted as real. Satellite data has confirmed their existence in multiple ocean regions. Researchers are still working to understand exactly where and when they are most likely to form, and whether the Western Atlantic has conditions that favor them. Some studies suggest that the interaction between the Gulf Stream and opposing winds can create the right conditions. Others note that rogue waves have been documented in many parts of the world, not just here. The science is active, and the answers are not yet complete. There is also the quieter work of historical review. Researchers continue to go back through old records shipping logs, military archives, weather reports, looking for details that earlier investigators may have missed. Sometimes a case that seemed mysterious yields a simple explanation when the original documents are read more carefully. Sometimes it does not. The historical record is incomplete in ways that may never be fully repaired. Ships that vanished before the age of radio left almost nothing behind. What all of this adds up to is a region that science has not finished with, not because the triangle is beyond explanation, but because the ocean and the atmosphere are genuinely complex, and the tools for studying them are still improving. Every year, researchers learn something new about how water moves, how weather forms, how the seafloor behaves. Whether any of those discoveries will finally settle the question of the Bermuda Triangle is something no one can say with confidence yet. The work continues. The question remains open, and that, in its own quiet way, is one of the most honest things science can offer. Over the past several decades, explorers and researchers have sent cameras, sonar equipment, and deep diving vessels into the waters of the Bermuda Triangle. What they have found is genuinely interesting. What they have not found is, in some ways, even more so. Modern sonar, the technology that uses sound waves to map the ocean floor, has given researchers a far clearer picture of what lies beneath those blue-green waters than anyone had just 50 years ago. The seafloor in this region is not a flat, featureless plain. It is a place of sudden drop-offs, long ridges, and deep trenches that plunge into darkness. Some of these formations were only discovered in recent decades. Others are still being mapped. The ocean floor here holds more geography than most people imagine, and much of it remains poorly understood. Underwater vehicles have explored some of the blue holes scattered through the Bahamian waters near the triangle's western edge. These are vertical caves, sometimes hundreds of feet deep, filled with layered water of different temperatures and salt levels. Researchers have pulled sediment cores from their floors, long cylinders of mud, and ancient material that record thousands of years of history. Those cores have revealed evidence of past storms, past sea level changes, past shifts in ocean chemistry. What they have not revealed is any clear sign of a force unique to this region that could explain unusual losses at sea. That absence of evidence is itself a kind of data, though researchers are careful not to treat absence as proof. Some expeditions have searched specifically for wreckage. The ocean floor in and around the triangle is not empty. There are indeed wrecks down there. Old wooden hulls, metal frames, scattered debris from vessels lost over centuries of Atlantic travel. But finding a wreck and explaining how it got there are two very different things. A ship on the ocean floor tells you where it ended up. It rarely tells you why it sank, or whether something unusual was involved. The sea keeps that part quiet. One of the more striking finds in recent years came from researchers using aerial imaging and sonar near the Bahamas. They identified unusual formations on the seafloor that some observers described as geometric shapes. For a brief time, speculation ran high. Some suggested these might be the remains of ancient structures, possibly from a civilization that predated recorded history. Other researchers looked at the same images and saw natural formations, the kind of angular rock patterns that form when limestone erodes in predictable ways. The debate was spirited, but no confirmed evidence of ancient human construction has been verified in those waters. The question of what those formations are remains, at least in some corners, open. Technology keeps improving, and each improvement changes what is possible to find. Side-scan sonar can now produce images of the seafloor detailed enough to show objects just a few feet across. Autonomous underwater vehicles, small robotic submarines that can dive without a human crew, can reach depths that were once completely inaccessible. Satellite data can track ocean surface temperatures, current patterns, and even subtle changes in sea level across wide areas. All of these tools are being used in the Atlantic, including in the waters of the Triangle. And yet, the central question has not been answered by any of them. No expedition has returned with a discovery that settles the matter. No wreck has been found with clear evidence of a force that defies ordinary explanation. No instrument has detected a persistent anomaly that appears only in this region and nowhere else. That is a significant thing to sit with. The tools are better than ever. The searches have been real, and the mystery, to the extent it remains one, has not dissolved under the weight of all that looking. Some researchers take this as confirmation that there is no special mystery here, that the triangle is a product of story and selection, not of any hidden force. Others argue that the ocean is simply too large and too deep for absence of discovery to mean very much. The seafloor of the Atlantic covers millions of square miles. The fraction that has been carefully examined is still very small. There may be things down there that no camera has reached yet. What explorers have found is a complex, layered, geologically active stretch of ocean with a rich and sometimes puzzling history. What they have not found is a final answer. The water remains wide. The depths remain mostly dark. And the question of what this place truly is, ordinary stretch of sea, or something that still holds a secret, drifts on, quiet and unresolved, somewhere beneath the surface. There is something quietly remarkable about the fact that we are here at all, sitting with an unanswered question, comfortable enough to wonder. The ocean does not need our understanding to keep moving. The currents do not pause while we debate their nature. The deep water turns and rises and falls on its own slow schedule, indifferent to every theory we have ever written down. And yet, we keep asking. That impulse, the need to look at a stretch of blue water and ask what is happening there, is one of the oldest things about us. Long before anyone gave the triangle a name, sailors were watching the sky change over that warm Atlantic water. They were feeling the compass needle drift. They were watching the horizon for weather that seemed to arrive from nowhere. The question was always there. We just eventually gave it a shape and a set of corners. What is strange about the Bermuda Triangle, when you step all the way back, is how much it reveals about the way human minds work. We are pattern-seeking creatures. We look for meaning in repetition. When ships go missing in the same general region across many decades, something in us wants that to mean something. It wants a cause, a force, a reason. the alternative that the ocean is simply large and dangerous, and that chance clusters in ways that feel significant, is harder to sit with. It offers no story, and we are creatures who need stories. Some researchers argue that is exactly what the triangle is: a story, a narrative we built over time, adding each new disappearance like a stone to a wall, until the wall looked like evidence. They point to the insurance data, which shows no unusual loss rates in that region compared to other busy shipping lanes. They point to the investigations that found ordinary explanations for many of the most famous cases: human error, sudden weather, equipment failure, the ordinary cruelty of the sea. But other researchers are not so quick to close the file. They point to the methane hydrate fields beneath that part of the ocean floor. They note the unusual geometry of the Gulf Stream, which can carry wreckage far from where a vessel actually sank. They mention the blue holes, those deep vertical caves in the shallow Bahamian seafloor, whose full depths have still not been mapped. They say the ordinary explanations are real, but they may not be complete. Both of those positions can be true at the same time. That is the quiet tension at the heart of this question. The ocean itself is not finished being understood. Scientists are still finding new species in the deep trenches. They are still mapping the floor of the Caribbean basin. They are still learning how methane moves through cold water under pressure, and what happens when it does not. The tools we have today are better than anything sailors carried in 1945. And still, the ocean keeps its secrets, not out of malice, simply because it is vast and deep and old in ways that are difficult to fully hold in the mind. The atoms in the water of the Bermuda Triangle have been cycling through this planet for billions of years. They have been ocean and ice and cloud and rain. They have been inside living things and inside stone. The calcium in the coral reefs of the Bahamas was once dissolved in ancient seawater, then built into shells, then pressed into limestone over millions of years, then slowly dissolved again. Nothing in that water is new. Everything is borrowed and returned. When a ship or a plane disappears into that water, it becomes part of that same slow cycle. The metal oxidizes, the wood dissolves, The organic material is taken up by the food chain of the deep. The ocean does not distinguish between what we have named and what we have not. It simply continues. That is not a frightening thought. It is, in its own way, a settling one. We are part of something enormously old. The questions we carry about the triangle, about the sea, about why things vanish and what remains, are the questions of creatures who are briefly awake inside a very long story. We will not answer all of them. Some of them will outlast us entirely. And that is all right. The water is still moving out there tonight. The Gulf Stream is carrying its warm ribbon northward through the dark. The blue holes are sitting in their quiet depths, full of water that has not seen light in a very long time. The question is still open. It will be open tomorrow. It may be open for a long time yet. That is not a problem to solve before sleep. It is simply something to carry gently, like a smooth stone in a quiet hand. And so we have come quietly to the end. We have traced the rough triangle on the map, from the tip of Florida down to Puerto Rico and across to Bermuda. We have watched the Gulf Stream pull its warm blue current through those waters, fast and restless, carrying away whatever the sea chooses to keep. We have sat with the stories of ships that went silent and planes that never landed. We have turned the questions over slowly, like smooth stones in a palm, none of it resolved. And that is all right. There is something honest about a mystery that stays a mystery. The ocean does not owe us answers. The sky does not explain itself. The deep trenches and the blue holes and the methane-laced sediment on the seafloor, they hold their secrets the way old things do, quietly, without apology. Tonight, let the questions rest where they are. Picture the Atlantic right now, in this very moment, while you lie still and your breath slows. The water out there is dark and deep and moving. The Gulf Stream is running north, warm and wide, maybe 60 miles across in places. Small whitecaps catch what little moonlight there is and then vanish. The surface looks calm from above. Below, the currents do their ancient work, carrying heat from the tropics toward cooler latitudes, the way they have for millions of years. Somewhere in those waters, the seafloor drops away into trenches that have never been fully mapped. The Puerto Rico Trench, the deepest point in the Atlantic Ocean, sits just at the edge of our triangle, nearly 30,000 feet down. That is almost 6 miles of dark, cold, still water pressing down on rock that no human eye has ever seen clearly. What is down there is mostly unknown, not dangerous, not threatening, just quiet and old and patient. The ocean has been doing this long before there were ships to sail it, long before there were names for any of it. And the sky above those waters is doing its own slow work tonight. Warm air rises off the surface. Somewhere, a small storm is forming and dissolving. The stars, where the clouds have pulled back, are very bright out over open water, far from any city's glow. Sailors used to steer by those stars. They memorized them the way we memorize the faces of people we love. Some of those sailors never came home. We talked about them tonight, the crews and the pilots, and the ships that went quiet. We held their stories gently, without drama. We acknowledged that the sea is powerful and that human beings are small in it. We also acknowledged that the numbers, when examined carefully, may not be as strange as the legend suggests. The mystery of the Bermuda Triangle may be partly a mystery of how stories grow, how a name once given to a place begins to gather meaning the way a reef gathers coral slowly, piece by piece, until the original rock is buried under something much larger. Or perhaps there is something else. Perhaps the methane, or the rogue waves, or the magnetic quirks of that particular patch of Earth are doing something we have not yet measured well enough to understand. The science is still being done. The ocean floor is still being mapped. The instruments are getting better every decade. We may learn more. We may not. That is the honest answer, and it is a peaceful one if you let it be. Not knowing is not the same as danger. It is simply the edge of what we understand so far. And the edge of understanding is one of the most interesting places a mind can rest. So let your mind rest there tonight, right at that edge. Picture the dark Atlantic water, smooth and wide under a soft sky. Picture the slow spin of the earth carrying those waters westward and then north. Picture the seafloor far below, ancient and still, holding its quiet geography in the dark. You are here, on this same planet, breathing slowly. The same forces that move the ocean are moving the air in your lungs. The same gravity that holds the water to the earth holds you gently to your bed. You are part of this system, this old and patient world, and it is not asking anything of you tonight. Just rest, just breathe. Let the questions float, unanswered and unhurried, out over the dark water where they belong. The triangle is still there. The mystery is still open. And the ocean, as always, keeps its own time. Subscribe for a brand new Earth topic every night. One tap, and something wonderful is waiting for you tomorrow. Sweet dreams.